This is classical theory of T electrons in solid. Uh, According to classical theory of T electrons in solid, the conduction electrons move in a random manner. So, if this is a block of metal, and in any metal, we know that there are free electrons, and if we consider any free electron, or we can say that if we consider any conduction electron, then this conduction electron will move in a random haphazard manner, just like the molecules of a gas in accordance with kinetic theory of gases. The molecules move in a random manner. Similarly, in case of a metal, the conduction electron moves in a haphazard manner. The electrons move freely without any potential. So, considering the fact that the electrons move freely without any potential, we can model this classical theory with the help of a particle in a potential box. So we can simulate this as particle in a potential box. So if this is the condition that the electrons move freely throughout the conductor without any potential, so we can calculate that what are the possible energies of an electron in a conductor. So let us first consider a, uh, a one-dimensional potential. So let us designate this as A and B, and potential, which is a function of x only, in our case is 0 inside A and B, and outside the potential is infinity. So this is the condition. We have modeled an electron which is moving freely inside a conductor to a particle in a one-dimensional box, and if we now solve that how the particle will behave in a one-dimensional potential, using Schrodinger's equation as h psi equal to E psi. So this is the time independent Schrodinger equation, and in our case as v equal to 0 within the box. So we can write the equation as 2m h cut square E psi equal to 0. Here psi is the wave function of the particle. Then, as you can see that this is a second order differential equation where alpha equal to root over twice m e by h cut. So as you can see that this is a second order differential equation, and if we solve this differential equation, we will get the value of psi as psi equal to a cos alpha x plus b sin alpha x, where a and b are the constants which we have to determine from the boundary condition. And so the boundary condition for the above solution is that the psi equal to 0 at x equal to 0. So we have designated the point A as x equal to 0, and we have designated the point B as x equal to b. So the boundary condition to determine the two initial condition is that psi equal to 0 at x equal to 0 and psi equal to 0 at x equal to b. So the reason why we choose this type of boundary condition is that as we have this potential equals infinity at the boundary, so we have assumed that the wave function of the particle must vanish at the two boundaries. So that's why we have written that at x equal to 0 our wave function must vanish, as because in this case we have an infinite potential, so the particle can't go beyond that boundary. So that's why the wave function of the particle must vanish at the boundaries. So now if we use this above boundary condition, then we will get that we will get as psi equal to root over 2 by L sine n by x by L. Here L is the width of the this box. In our case the width is a, as you can see that it is from x equal to 0 to x equal to a, so we can write 2 by a sine n by x by a. So this is the wave function of a particle in a one-dimensional potential box. And let us now calculate that what are the allowed energies. So the allowed energies, if you compute the allowed energies, then it will be n equal to n squared pi squared h cut squared by twice m a squared. Here n equal to 1 2 3 dot 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 dot, and a is the width of our potential box. So this is the allowed values of energy of a particle in a one-dimensional potential box. So now if we draw that how our wave function will behave in a particle having a one-dimensional potential, then we have our ground state as n equal to 1. So this is for n equal to 1. This is for n equals 2, and for n equal to 3, this is for n equal to 3. So these are the behavior of a function in a particle in a one-dimensional potential box, and this is the above energy values of a particle. So from the expression of energy of a particle in a one-dimensional box, we see that the energy of a particle is quantized. The particle has quantized energy, which is in accordance with quantum theory. Later on we will see that this classical theory of electron can't explain several other phenomenon, for which we have to accept another theory called chronic theory of electrons, which can explain the behavior of conduction electrons in a metal easily.